Thanks a lot. Yeah, so I'm going to be talking about key transparency at Proton and specifically in Proton Mail. So I will... okay. So I sort of assume that a lot of people in the room already know what key transparency is and sort of how end-to-end encryption works and so on, but I'll very quickly go through the problem statement and just to make sure that everyone is on the same page, and for the people watching online perhaps that are maybe not as familiar, I'll sort of very briefly go through how does our encryption work. Is basically when you send an email, or also when you share a folder or file in Proton Drive, or when you share an event in Proton Calendar, you look up the public key from Proton server and encrypt the message or the file or whatever it is with the public key and send it to them, and then they can decrypt it, which is great. However, there is a problem, which is that if the server wants to do a man-in-the-middle attack, it can give you a different key, and then if you encrypt it with that key, then the server can read it, or the wrong person can read it. And in fact, it's really difficult to detect this because the server could re-encrypt the message with the actual key of the recipient, and the recipient would be none the wiser, and the sender would be none the wiser. So it's actually fairly difficult to prevent this attack. So until now, the way that or the solution that we've had in place to prevent this is something that we call key pinning. So you can trust a specific key, for example, after you manually verify the key by, let's say, calling up your friend and saying, hey, I'm seeing this key with fingerprint DBD12 and so on. Is that indeed your key? And then they say yes, and then you click, trust the key. And then after that, if the key ever changes, we'll warn you, and you can call them up again. But of course, this is a very manual process, and most people won't do this. Although a while back, when I looked up some statistics for internal messages, the number of internal recipients that used key pinning was actually around 30%, which is a lot higher than I had expected, but it's still obviously a lot lower than 100%, and we would like to protect 100% of our users. So that's basically, that's where key transparency comes in. It's basically intended to be a much more automatic a way to protect users against this attack. So the very high-level protocol, or very high-level idea, is that we publish all keys for every Proton mail address, and then every user. So we publish it to a transparency log, and then every user will go and check their own keys in this transparency log and check that they match their own keys. And then when sending a message or a file, you also go and check the keys that you receive from Proton's key servers against this transparency log. And assuming that the recipient has checked their own keys, and assuming that you're seeing the same keys, given that it's in a public transparency log, you can know that they are the correct keys for that email address, and that you're encrypting hopefully with the right keys. And it's important to note that this gives you a slightly different guarantee than key pinning, in the sense that you only know that the keys are the correct keys for that email address, at the point as long as the sender is, continuously verifying them and warning you if they ever change, because the owner of the key is the only person that can know whether they're correct. Whereas with key pinning, you're warned immediately if the key changes, and then you can, as I said, go and call them up. So this is a detection mechanism rather than a prevention mechanism. But nevertheless, that's sort of the trade-off with it being an automatic system that can protect everyone by default without having to do any manual action and without impacting the user experience. But nevertheless, it's it gives you a lot more security than doing nothing. And also, in my mind, it's sort of a deterrence mechanism as well, to hopefully dissuade the server from trying to do a man-in-the-middle attack in the first place, because it might be detected, right? So, a brief history of... Oops. I keep forgetting to switch both. Brief history of the development of key transparency at Proton. We started in late 2018 with developing a version of key transparency based on Konix. Then, we spent some time on it off and on. We didn't work on it continuously from 2018 till 2023, development happened, took a while. It turned out, to be quite a large project. Also, since we developed our implementation from scratch, so was quite some work. Eventually, in 2023, early 23, Tore Goebel from ETH Zurich came in and did a project. Well, we did a project with them. And he brought in some ideas, particularly from the Seamless and Parakeet papers, and we adopted some of them. So that I would say improved the system a bit. And then late 2023, we launched in beta. It's still opt-in, even today, which I'll get to later. But you can use it. No worries. And in earlier in this year, we published a white paper together with Tore Goebel, sort of describing how the whole system works. So I'll have a link at the end of this talk in case you want to have more details. So I'll go through each of the. I'll go through each of the 3 steps briefly. To each of the steps that I highlighted in the high-level protocol, and dive into a little bit more detail to see how they work. So first of all, for publishing the keys, what we do is every 4 hours we publish what we call an epoch, which is basically a Merkle tree of all the keys, the history included, of all the keys of every email address at Proton. I'll show the structure in the next slide. And then we compute the root hash of the Merkle tree and the chain hash, meaning the hash of the root tree and the previous root tree, so that we include the entire history. And then we request a TLS certificate for the chain hash under some domain. Of course, we've already had quite some interesting discussion about the use of certificate transparency to bootstrap our trust here at this summit, and probably there's better things we could do in the future, but for now this is the way that we bootstrap our trust in key transparency is by piggybacking on certificate transparency. So basically, the certificate with the chain hash gets published in certificate transparency logs, and auditors can go and check that we've only published one chain hash for a given epoch. So here is the structure. Well, here is the structure of the tree. So basically, we have a tree of 256 levels. The path of the first 256 minus 32, the top layers are determined by a VRF of the email address, and then the lowest 32 levels are determined by the revision. So we have a single tree for all the versions of all the keys of everyone. For historical reasons, we start at revision 1 instead of 0. So revision 0 at the very bottom left is always empty, which is sort of a historical accident, but we can, we could at some point we could use it to do something special there. But for now, it's always empty. So at revision 1, you have the sort of the first version of the set of keys for that email address, and then at the next revision you have either the next version, or in this example you might have what we call an obsolescence token, which is just a token saying this email address has been disabled, for example. So then the auditors, we rely quite heavily on external auditors in our key transparency scheme. So they have to check a couple different things. First of all, as I said before, they have to check that there's only one root hash or chain hash per epoch ID in the certificate transparency logs, because otherwise we could show two different trees to different people at the same moment. Then they have to check that all the epochs form a consistent chain, and they have to check that the subtrees, meaning the lower portion of this tree, are append only with an asterisk, meaning that for stale entries, which are revisions that have been unused for more than 3 months, they can be removed. Epochs that are older than 3 months currently cannot be verified anymore anyway, because the certificate from Let's Encrypt will have expired, even though in the future that might change. But I think having some mechanism to purge old entries is also useful. So then we go to the next part of the protocol, which is once we've published all these keys, every user of Proton will have to verify that their own keys matches what we have published. So the procedure is basically you have to regularly fetch the latest epoch and verify the certificate that has been requested for this epoch, and check that the fingerprints of your key in the latest revision match your own private keys. And the private keys, we encrypt them with their own password. So assuming that only you know your own password, you can know that they're your keys, and therefore you can check that the correct keys have been published. Then you also have to check that any previous modifications that you made to your keys are included. So whenever you create a new key or you mark a key as obsolete or whatever, we create a local artifact that we call a signed key list that you basically store locally that says, well, I've updated my keys, so I'm going to check later that they were actually included in the key transparency log. And we have a maximum merge delay similar to certificate transparency, although in our case for now it's 72 hours. Because we don't like to be waking up on the weekend, but we hope to one day, bring it down as we're more confident in the stability of our log. Then you also have to check that additional changes that were not made locally are properly signed and are correct. Because in our system, you may have multiple devices, so you can change your keys on any of those devices. And that's, again, where the signed key list comes in. I'll actually think I have a slide about that. So yeah, this is what the signed key list looks like. It's basically a signature plus the data, which says, here's the list of keys. Each of them will have a set of fingerprints, which are like the OpenBGP subkeys fingerprints, which are hashed using SHA-256. And then they say, well, whether the key is primary or not, and the flags, which are like, is this key obsolete or not, for example. This data structure is created every time you make any change to your keys, and is stored also on the server. And then when you log in on a different client, you can check that the change that has been made to your keys is correct, as long as the primary key, which is the first key in this list, is still included in the new change. So if you have like a clean break, let's say you forget your password and you reset your password and you generate an entirely new set of keys, then obviously the new signed key list will be signed by a different key, and you actually can't check that the previous revisions in the key transparency log are actually correct, because you don't have the key to verify them anymore. And in that case, we have to warn the user. But hopefully they will know that indeed they had reset their password, and that that is expected. If they hadn't done that, then that might indicate some kind of attack, right? So then here are some screenshots of the what we call the self-audit, but perhaps more aptly named self-monitoring in Filippo's parlance. So here's the UI. So first of all, we have a setting to enable key transparency, and once you do that, you get an option in the settings drop-down that you can go and look at and see that indeed your own keys have been correctly verified in the key transparency log. And you can see a list here of the addresses that has been checked for, and that's actually relevant for security in our case, because you might have multiple email addresses in your account, and whenever you log in, the server actually tells you what those email addresses are that you have, and if the server were to hide one, then the self-audit or the self-monitoring wouldn't run for that address, and then you might miss some malicious changes to the keys for that address in the key transparency log. So for now you have to check that the self-audit was done for the correct addresses. We have an idea to fix that by having a signed address list that basically authenticates what your list of addresses is whenever you make a change, or when one of your addresses gets disabled, for example, you would get a warning saying, sorry, this address has been disabled, and therefore we can't audit your keys for that address anymore. And that also means that you would have to go and warn your contacts, for example, that if they send email to that email address, it's no longer necessarily secure, right? Because all of this entire key transparency model only protects you as long as you own the email address and you're able to audit the keys for that address, right? As soon as the ownership changes, then a different account is in control of those keys, and then it's expected that those keys will change. So if something fails, then the user interface will look like this. You'll get an error dot and a warning or an error in the dialog saying something went wrong with verifying these keys, and then you will have to perhaps go on Reddit to complain, saying that well, hey, maybe Proton is trying to attack me, or perhaps there's a bug. Probably the latter is more likely, but yeah, eventually we'll have to get rid of all of those bugs to make sure this never happens, but we're not quite there yet, which is why it's still opt-in. So then for the third part is verifying the public keys of other users when you send them an email. And there the user interface looks like this. Well, basically what you have to do is you just fetch the keys from the key server as normal, and you fetch the latest epoch and verify the certificate again, and check that the epoch includes the public keys that you got in the latest revision. And when it happens, you get a nice blue lock. If that doesn't happen, you get an error. So here we're aiming for having no indication in the positive case and having a negative indication, in the error case, rather than requiring the user to look for and check for like some kind of positive indication, like a check mark. Also because we already have a check mark for pinned keys, so we didn't want to have like two different indications or two different check marks that the user would have to look for, right? So there is an edge case here, which is if the recipient keys recently changed. You might remember that I said at the beginning that we issue an epoch every 4 hours, which is quite a long time, and during that time the keys might change. And in that case, you get the signed key list that user created and store it locally as well. We still accept the keys and we still show a blue lock, but in the next periodic audit, so this is like at the same time as you're doing the self audit or the self monitoring, you also check the signed key lists that you got for other users and check that they indeed were included in the next epoch, or at least within an epoch in the next 72 hours. And if that doesn't happen, you again get an error in the same place as the self audit error, saying that you got a key for some address that actually was not the one that ended up being included in key transparency within 72 hours, and it tells you to go and check the keys. Although there is an interesting UX problem here, which is that if you actually go and check the keys, at that point, they might actually be correct, because the server could serve you different things at different times. So actually, the only thing this error really tells you is that at some point in the past, you got some wrong keys, and we have the fingerprint of those wrong keys, but we don't have the keys. So it's actually still a little bit of a UX challenge, I would say, to perhaps more clearly explain to the user what might have gone wrong, especially since we don't really know what went wrong, right? We just know that something went wrong, and either the server might have been malicious, or there might have been a bug. Again, we would like to get rid of those bugs, but we're not quite there yet. So there are a few other interesting edge cases. Yes, good, thank you. So one is around deleted and transferred accounts. Here is a screenshot, a redacted screenshot I got in a bug report from our CEO, Andy, who said, here's an email I got, and I see a warning, and the warning is, the warning was because the account had been deleted, and so we could no longer verify the keys and verify the signature. So we ended up saying that, as I was alluding to before, key transparency can only protect you as long as the sender owns that email address, right? So nowadays we no longer show this warning, and basically, if someone no longer owns the email address, they basically have to tell you, don't send me email there anymore, because now that email address belongs to someone else, right? Then there's a whole bunch of other issues. I won't go through all of them, also for lack of time. Some of these are legitimate bugs. Some of them are just weird things in the web app. Stuff like type error, cannot create property 10 on number 9. That's not like that's not really explainable. Like the best theory I have is that there is a web extension doing something strange to our web app, causing us to, causing strange errors to be thrown. Others might be legitimate bugs that we still have to fix. But there's a whole bunch of false positives here that we still have to reduce before we can enable it by default. Then there is the white paper I was mentioning at the beginning. So here's a QR code. You can go and read the white paper if you want more details. And that's all I have. So thanks a lot.